Excellent. All right, so this is the 7th lecture of Math 313 number theory. And so what we're going to do today is we're going to start with Fermat's little theorem. We're going to talk a little bit about generalizations. And then we're going to go into solving equations. And we're going to solve equations on the clock with modular arithmetic. So remember, Fermat's little theorem, and I like to use a lowercase l to remind us it's a little theorem, is if A and P are relatively prime, then, so that means basically this equals 1, then A to the P minus 1 is congruent to 1 mod P. You could write A to the P is congruent to A mod P. And so again, what mod means is we say, x is congruent to y mod n means x minus y is a multiple of n. So on a clock, 10 and 10 plus 5 would be different numbers. 10 plus 5 is 15, but it's also 3 because 3 and 15 differ by 12. They differ by a multiple of 12. So when we look at this, this is a little bit nicer. The A to the P is congruent to A mod P because I don't have to worry about our A and P relatively prime. All right, so we gave two proofs of this. The first proof was was using the factorials, and the second was the binomials. Okay, and then the question is, which proof generalizes, and how should we generalize it? So we had two proofs. One, we used basically P minus 1 factorial, and the second, we used P choose K was a multiple of P if 1 less than equal to K less than equal to P minus 1. So we'll see one of these generalizes very nicely, one of them does not. The other question is, let's look at A to the P minus 1. So we saw that this could be a primality test, right? If I calculate A to the P minus 1 and it's equal to 1 mod P, a number might be a prime. And the more numbers I check, the more A I check, maybe the more confident I become that it's prime. Unfortunately, it turns out there are infinitely many exceptions. There are infinitely many composite numbers that will pass this test for every n. For every A. And these are called Carmichael numbers, and some of your homework problem is to write some code to explore this. It's annoying that they exist. But if we calculate A to the P minus 1 and it's not 1 mod P, what do we know? It's not prime. So at least if the test says composite, we can trust it when it says composite. It's not going to lie to us. Unfortunately, there will be times when it says, I don't know. I think it's prime, pretty sure it's prime, but I could be wrong. There is another test, which is one of your homework problems on Wilson's theorem, which is a completely deterministic way to get a primality check. The problem is it's horribly inefficient. So the first thing here is, how difficult is it to calculate A to the P minus 1? So let's say we are looking at a prime that's around 200 digits. And we want to compute A to the P minus 1 mod P. Okay? If you've never seen this before, this should be scary. Approximately how many multiplications do we need? So if we want to compute, let's do something a little bit easier. Compute x to the n. How many multiplications? Let's say we do 100. How many multiplications? 99. Okay, so it's not as bad as 100, right? Because x squared is x times x. X cubed is x times x. So 99 multiplications. So here, if we have p around 10 to the 200, which is what we would need for cryptography, we're talking on the order of 10 to the 200 computations. We talked earlier in the semester about, imagine every subatomic doohickey in the universe is a supercomputer devoted exclusively to us, running since the dawn of the universe, and we're not even close to 10 to the 200. And so we want to raise something to the 10 to the 200th power. Now, we are taking things mod p, so we don't have to keep storing the whole numbers, so they won't grow too much. But still, this looks intractable. And so the only reason that this is feasible is that there's a fast way to do this. So this is one of the themes in this course. It's not just to write down a method. It's to write down a method that's good, that's practical. So we're going to do, we've talked about different bases. We're going to look at base 2. So binary. I can write 100 as 64 plus 32 plus 4. I always use 100, so I always remember what the binary expansion is. So here, when I write a number in binary, instead of writing it as a multiple of 1 plus a multiple of 10 plus a multiple of 100 plus a multiple of 1,000, I'm writing it as a multiple of 1 plus a multiple of 2 plus a multiple of 4 plus a multiple of 8 plus a multiple of 16. So when I write 100 in base 2, I get 64 plus 32 plus 4. Or if you want to write it the long way, it would be 1 times 2 to the 6th, I think, right? Plus 0 times 2 to the 5th, plus 0 times 2, oh no, sorry, plus 1 times 2 to the 5th, plus 0 times 2 to the 4th, plus 0 times 2 cubed, plus 1 times 2 squared, plus 0 times 2 to the 1, plus 0 times 2 to the 0. So this would be writing the number in binary. If I really want to write the digits, I could write 1, 1, 0, 0, 1, 0, 0, and put a little subscript 2 there to tell us I'm writing it in binary. Why is this helpful? Well, the reason this is helpful is x times x is x squared. X squared times x squared. X to the 4th. X to the 4th times x to the 4th. X to the 8th. X to the 8th times x to the 8th. X to the 16th. X to the 16, x to the 16 is x to the 32. And then x to the 32, x to the 32 is x to the 64. 1, 2, 3, 4, 5, 6 multiplications to get here. 7 to then multiply by x to the 32, and then 8 to multiply by x to the 4. So we can actually calculate x to the 100 in 8 multiplications. So the cost is 8 multiplications, not 99. That's an incredible savings. There is a little bit of a disadvantage. What's the disadvantage? It's a little subtle. This does have a slight drawback to just straightforward multiplication. Yes?
So you have to go back and forth between binary and...
So you do have a little bit of the conversion. You have the conversion at the end and the conversion at the beginning. Although if we're working with computers, computers would probably prefer to work things in binary, and it's this stupid human interface that requires the base 10. But there is that conversion factor, and there is the cost of calculating what the binary expansion is. But the binary expansion of a number is not that bad to get. But that is a cost. There is another cost. It's storage. We're storing all these values. A better way to do the calculation is we don't have to keep things stored. Once we calculate x to the 4th, do we need to store this value anymore? No, because we just keep the numbers that are in the expansion. So we would have x to the 4th, and then we would multiply x to the 4th, get x to the 8th. We have to keep x to the 4th because that's in our expansion. Then we get x to the 16th. We keep x to the 4th and x to the 16th. We calculate x to the 32nd, and now instead of saving x to the 4th, we would now save x to the 36th and x to the 32nd. So we can do a little bit better job managing space, which is worthwhile. So the true cost is about maybe, I think, like 2 log base 2 of n at most for x to the n. And it's because we have something like this that it's feasible to work with large primes. If we didn't have something like this, it would just be a theoretical oddity. There are generalizations, there are related ideas like this. You have a whole class talking about how to evaluate a polynomial quickly. It turns out there's faster ways to evaluate a polynomial than brute force. This is a very special type of polynomial. There's just one term. And because of that, there's an even faster way of evaluating this. So I'll put some additional reading. All right, so that's just one thing I want to talk about, is that while this might look painful to do, it's actually really fast to calculate this. The log of 10 to the 200 is 200 log 10. What's the log of 10? We're taking the log base 2. All right. What's the log of 10 base 2 approximately? 3.2. 3.2. Great. All right. So it's 3.2 times 200. That's less than 700. We can do 700 multiplications. That's not too bad, especially since we're reducing things mod p. We could even do things of size 10 to the 2000. Working with such large primes won't be so bad. All right. So that was the first thing. The second thing, so what could a to the p minus 1 over 2 be? So the first thing is, does a to the p minus 1 over 2 always make sense? For prime p. So p is a large prime, i.e. at least 3. Okay? So for different problems, large means different things. For some things in an elliptic curve, large means 5. For a lot of this stuff, 2 is special. And we'll see later why the prime 2 causes a lot of problems. All the other odd primes are very nice. So if p is odd, p minus 1 is even, so I can divide by 2. What can you tell me about a to the p minus 1 over 2? And I'm jumping ahead. This is not, we're not supposed to meet this until chapter 3 in the book. But as long as we're here right now, what do you think could be true about a to the p minus 1 over 2? Any thoughts? What could its possible values be? So do you have a guess?
No, I was just thinking about.
Okay.
Well, it's 0 through p minus 1.
So good. So we know it's 0 through p minus 1.
Is it p minus 1 over 2?
Well, what do we know? Do we know anything about any relationship between a and p? What do we know about the relationship between a and p?
They're relatively prime.
They're relatively prime. What else do we know?
A to the p minus 1
Is 1 mod p. So how would you view a to the p minus 1 over 2?
That squared is 1 mod p.
So basically, this squared is 1 mod p. So I'm essentially asking, if this number is 1 mod p, I'm asking for its square root. What are the possibilities? 1 and negative 1 are definitely possibilities. Are there anything else? So p is prime. So this leads to the interesting question of solving polynomial equations. And so we know how to solve polynomial equations over the integers. This is not that mysterious. All right, so I apologize if some of this seems review. It's not because we have people from high school that I'm going back to high school math. This was planned previously. I want to look at how we solve equations over the integers, over the reals, and then see what changes when we look at things over these clock groups. And big chunk of your homework this week is to write some programs and numerically explore and get a sense of what the answer should be. So let's try to solve. I want to just do things the same way I've written things here. Right. Solve ax plus c equals 0. Let's solve a linear equation. Is this hard to solve a linear equation over the reals? No. We just subtract c divided by a. We get x equals negative c over a. Right. Not that bad. Unless a equals 0, in which case we can't do this. So I'll assume a is not 0. The next thing is to try quadratics. Let's start off with an easy quadratic first. Ax squared plus c equals 0. And then we'll see, once we know how to solve this, we will try to reduce a general quadratic to this. What's nice is we can solve this using the same technique as before. We get ax squared equals negative c, x squared equals negative c over a, so x is going to be plus or minus the square root of negative c divided by a. Now, an important thing to note is that this may not be a real number. So for example, x squared plus 1 equals 0, you get x is I and minus I, where I is, or I am, the square root of negative 1. So the reals are not closed. You can have a polynomial with real coefficients, but the answers could be complex. What if I gave you a more general quadratic? What if I gave you ax squared plus bx plus c equals 0? What we would love to do is write this as like ax plus h plus d equals 0 squared. Because if we could write it like this, we know how to solve something like this. The solution is going to become, x plus h squared is negative d divided by a, so x will be negative h plus or minus the square root of negative d over a. And this is where the method completing the square comes from. We know how to solve simple quadratics, so we want to choose h and d such that these two are the same. So find h and d. And so we would get ax squared plus 2ah plus h squared plus d squared is equal to ax squared plus bx plus c. So this, this should be 2ahx. So this part over here has to be b. And then this part over here has to be c. Well, what's nice is we have h and d are free. So if you give me b, h is just going to be b divided by 2a. And now that I know what h is, and I know what c is, I can solve for d. And so we would get, so we get d is equal to c minus h squared. I'm not going to go through and do the algebra. I think you can all sing-song the quadratic formula from this point onward. It turns out that there is a way to solve the cubic and write down the closed form expression for the roots of a cubic. There is one for the quartic. There is not for the quintic and higher. There's no closed form expression for a general quintic. Beautiful, beautiful theorem. Okay. The last thing to just remark is we've talked about fundamental theorems. We've done the fundamental theorem of arithmetic. There is the fundamental theorem of algebra. Right? Anybody tell me what the fundamental theorem of algebra is? Good. So a polynomial of degree n has n roots. So fundamental theorem of algebra, polynomial of degree n has, I'm going to add one word to what you said, I'm going to add exactly n roots. And the roots may not be real, they could be complex. The coefficients of the polynomials could be complex. It's a surprisingly difficult theorem to prove. My favorite proof of this uses complex analysis. Wonderful, wonderful subject. But we've had this result for a long time. So any polynomial of degree n has exactly n roots over the reals, or over the complex. Let's look at x squared minus 1 is congruent to 0 mod 12. One squared is, so 1 works. 2 squared is, well, okay. If the number has anything in common with 12, then its square will have something common in 12. And since 1 is relatively prime to 12, its square minus 1 can't be 0 mod 12. So I don't have to check any number that shares a factor with 12. I only have to check the numbers that are relatively prime to 12. So I don't have to check 2, I don't have to check 3, I don't have to check 4. 5 squared is 25 minus 1 is 24, which is? Okay, 6 I don't have to check. 7 squared is 49 minus 1 is 48. Also, when I subtract. Okay, 8 I don't check. 9 I don't check. 10 I don't check. 11 squared is 121 minus 1 is 120. Wow. Fundamental theorem of algebra fails miserably. We have 4 solutions. What should we do? I really hate losing the fundamental theorem of algebra. It's such a nice theorem.
Well, it's only over the like the complex numbers. It doesn't refer to like modular.
Yeah, so the question is, where else does the fundamental theorem of algebra hold? If I'm looking at z mod 12z, it fails miserably here. Yes?
Should we try making our, instead of using 12, use an actual prime?
Oh, let's use a prime number. So let's discriminate and say that any composites are not allowed to come to the party. We will not consider them right now. And so now, we want to solve x squared is congruent to 1 mod p. Okay? So this means, x squared minus 1 is congruent to 0 mod p. We can factor this. This is x minus 1 times x plus 1 is equal to a multiple of p. Right? That's what it means to be congruent to 0. But now we have our wonderful fact. What wonderful fact do we have? P is prime. And so how does the primality of P help us?
Either x minus 1 or x plus 1.
Good, because P is prime, if a prime divides a product, it has to divide one of the two. And this is what was going wrong with 12. Because when we had 12, it's a multiple of 12. Maybe 4 divides the first factor and 3 divides the second, and that gives us a lot more possibilities. Because P is prime, if this is equal to a multiple of P, so P divides x minus 1, or P divides x plus 1. Well, the possibilities for x goes from 0 to P minus 1, so what does this tell us? X equals, what's the only x that will work? So we've got to have x between 0 and P minus 1, and x minus 1 must be multiple. So the only possible multiple would be 0. Because if x was as large as P minus 1, you'd get P minus 2. So the only possibility is x equals 1. What about over here? What's the only possibility? X equals P minus 1. So in this case, it's restored. We only have 2 roots. So the question is, will we always have 2 roots? Will the fundamental theorem of algebra always hold? This is just one data point. But at least we did the data point for all primes. We didn't just do it for 7 by doing a brute force calculation. We now know for any prime, x squared congruent to 1 mod p will have 2 roots. What about x squared plus 3x? Will that have 2 roots? We haven't done that yet. And which prime might be a little bit dangerous? 2. Do you know why 2 might be dangerous for solving quadratic equations? I'm sorry? So 1 and P minus 1 are the same, so things could be collapsing, but maybe it's a double root. So that's definitely a possibility.
X is equal to x squared.
Okay, x is equal to x squared. Why is that bad?
Because then you're really solving, you're not solving the
So now we're solving a linear equation.
linear.
There's another reason. I didn't write the quadratic formula. But the quadratic formula has 4 and it has 2 in it. The 4 isn't so bad because that's in the numerator, but in the quadratic formula you have a 2 in the denominator. That's the 2 inverse. If we're looking at the prime as 2, 2 inverse doesn't exist. So there could be some issues with when P is 2. Okay, so the whole point is that solving equations in these clock settings can become very challenging. And that's why I want you to write some code, and I want you to explore some things and make some conjectures. You look at the data and try to guess, when do you think you're going to have a certain number of solutions? How many solutions do you expect to have on average? Yes?
So since you said that over where we had like x minus 1 times x plus 1 is compared to a multiple of p,
Yes.
that like p had to divide
Right.
Would you say that, or would it be reasonable to conjecture that there are two roots for each prime factor of composition?
So what you might want to say is that, if we have a number, maybe instead of having p, maybe we had 6, which is a product of two primes. Then this could have two possibilities, this could have two possibilities, but they have to be holding simultaneously.
Right.
So for instance, this would maybe be a multiple of 2, this is a multiple of 3, but they have to hold at the same time. So that's where things get challenging, is how do you know that you can do this at the same time?
The solutions you gave out
Yes?
for the next one.
Oh, did I give them up? Oh, okay. If I give them up for the next homework, don't look at the solutions. There was an issue with the printer this morning, and so don't look at the solutions. Thank you. Okay, I will print out the correct ones later. Okay, so it's a good idea to try to conjecture. And what I would do is I would look at a bunch of composites, and I would try first product of two primes, and see if that's easier than something like 12, which has 2 squared and 3. But you're going to need things to be happening simultaneously, and that's much harder. Here, I just need one of these to hold. Okay. So the whole point is we're trying to get some sense of what's going on. We want to figure out how we generalize things. And so we're going back, and now we want to know is what happens, what about a to the, I don't know, we'll call it f of n congruent to something mod n. Is there a generalization if n is composite? We know that f of n should be n minus 1 if n is prime. The nicest thing is if the something could be identical for all n. What would you love that identical thing to be? 1. Because we know it's got to be 1 when it's a prime. So the question is fn always n minus 1, or is it something else? So this is going to be Euler's theorem. If a and n are relatively prime, then a to the phi of n is congruent to 1 mod n, where phi of n is going to be the number of k 1 less than equal to k less than equal to n minus 1, such that k and n are relatively prime. Or if you want, it's the size of the group z mod nz star. This was the elements that are relatively prime to n. So this is the Euler-Toshen function. We've talked about this before. Now what's nice is if n is prime, how many numbers from 1 to p minus 1 are prime to p? All of them. With 12, how many numbers are relatively prime to 12 from 1 to 11? 4. And so we would then be getting things like a to the 4th should be congruent to 1 mod 12. We've actually already proved this. Because the only numbers relatively prime to 12 are 1, 5, 7, and 11. We've shown that their squares are all 1 mod 12. So their 4th power is the square of the square. If the square is 1, the 4th power is 1. So we've verified that this is true when n equals 12. So this is worth remarking. We did for n equals 12. Only check a in 1, 5, 7, and 11 all have a squared equivalent to 1 mod 12. So a to the 4th is equivalent to 1 mod 12. So we have at least one data point. And it's a non-trivial data point. It's a really nice composite moduli. And it tells us that the generalization can't just be n minus 1 as the power. N minus 1 is not always going to work. Why not? Well, if we tried n minus 1, maybe that works too. So what would 5 to the 12 minus 1 be? That's 5 to the 11. That's going to be the same as 5 to the 10th times 5 mod 12. Right? What do we know 5 to the 10th is congruent to? It's 1. So this would be congruent to 5 mod 12. So one of the possibilities which we did have to eliminate is maybe a smaller value of fn works if n is composite. Maybe we don't have to go all the way up to p minus 1. Maybe something kicks in earlier. But we've just shown that we know it's not going to hold now for a to the n minus 1 for all a and n relatively prime, because 5 to the 11th is not 1 mod 12. So this tells us we do have to do a lot of work. And this explains why I wanted to do that digression in the beginning, looking at, well, what could we say about maybe a to the p minus 1 over 2? And what are the possible values for that, trying to get some intuition. Maybe things kick in at a lower level, but it doesn't matter if they kick in at a lower level. When we build up to a to the p minus 1, it should still be 1. Okay, so if you know group theory, this is trivial. So how many of you have taken abstract algebra? All right. Have you seen the proof of this from abstract algebra? Okay. What's the proof of this from abstract algebra? Somebody who hasn't spoken today, you want to say the abstract algebra proof? I was never in abstract algebra, so. Whose theorem is this from abstract algebra? Anybody remember? This is Lagrange's theorem from abstract algebra, right? Lagrange's theorem says that if you take any element in a group, or if you take any subset of a group, the order of the subgroup divides the order of the group. Look at the subgroup generated by the element A. So you get 1a, a squared, dot, 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 and then a to some power. The order of the group here is phi of n, so it's got to divide. So that means if you raise it to the phi of n, it's got to be 1. So I'm not going to go through it. I'm not going to write Lagrange's proof on the board, but if you remember your abstract algebra, that's how you would do it. It's just Lagrange's theorem. Okay. This is not a class with abstract algebra as a prereq, which is good because I have not taken it. And your professor should at least have the prereqs for the class. So that means there should be a way to do this. And this allows me to talk about why we gave two different proofs. So we gave two proofs of Fermat's little theorem. We did the p minus 1 factorial, and we did the p choose k. There's no wrong answer, but there is an answer that's more right than the other. Which proof is better? Which did you prefer? Now, better could mean different things. If you only care about Fermat's little theorem, I actually liked the p choose k proof. I thought that was really nice and slick, using the fact that p choose k is a multiple of p for such k. And this is in some sense what it means to be prime. And I got to get a real sense of where primality was coming into play. You know, it's about p being prime. And I can see primeness here. The p minus 1 factorial, I didn't really see the primality coming into play. I did not see where p had to be prime. I just saw a calculation, and at the end of the day, everything canceled and everything worked. But this proof, I did not really see the fundamental role that prime played. So if we just care about Fermat's little theorem, which proof do you think is better? And of course, you're free to choose either one. Oh, good, we all choose this, right? It even has the word choose in it, right? So we should, of course, choose p choose k. Which do you think will be better to generalize? So now we replace p with n. We have n choose k. Oh, dear God. We've now got to figure out, when is n choose k a multiple of n? That could be very complicated because if n is composite, different things could now be dividing up and killing that factor of n. We knew that the p up top wasn't canceled with anything down below, but now we can have cancel them. This is going to generalize a lot better. So in terms of proving Euler, this is the way to go. Okay, so let's prove Euler. Proof of Euler. All right. So we can revisit the proof we did before. What did we do before? We took some number a, which was relatively prime, and we looked at a, 2a, 3a, 4a, and all that stuff. Right? And when we multiplied them all together, we got, the old proof was we got a times 2a times 3a times p minus 1a was congruent to 1 times 2 times 3 times p minus 1 mod p. And the whole point was these numbers were all distinct residues. And so since they were distinct, that's just the numbers 1 through p minus 1 in a different order. And so we would then get a to the p minus 1 times p minus 1 factorial is congruent to p minus 1 factorial mod p. Since this is relatively prime to p, we can cancel. If you want to do it the long way, we could subtract and do a to the p minus 1 minus 1 times p minus 1 factorial is equivalent to 0 mod p. P can't divide this, so p must divide this, so this must be congruent to 0 mod p. That was the old proof. So we want to see how to generalize this. So the idea is to maybe look at some kind of product and just show that the products will be distinct. Okay. So we're now doing Fermat's little theorem. We're now doing proof of Euler. And so the claim is a and n are relatively prime, implies a to phi of n is congruent to 1 mod n. And so we're looking at now z mod and z star. This is all k, 1 less than equal to k less than equal to n minus 1. K and n are relatively prime. If you are wondering who cares, this generalization is what's needed for RSA. So one of the gold standards for cryptography for decades involves having to calculate something like this, where n is going to be composite. N will typically be the product of two primes. So this is not just we've got a semester to fill. Euler's pretty famous. When in doubt, throw in a result of Euler or Gauss, and you can't go wrong if you're building your syllabus. This is something that has incredible applications. All right, so we want to figure out how this is true. What might we try to multiply? Yes? Well, the problem is if we do phi of n minus 1 factorial, we're going to have some numbers that are not relatively prime to n, and we'll get 0. So we can't just, so the most natural thing is to just do a, 2a, 3a, 4a. We can't do that because some of those numbers now share a factor with n. So what could we do instead? Yeah, let's just do all the things in this. So let's call this set maybe G1, G2, G phi of n minus 1. We'll call those our elements. So now let's do G1 times A times G2 times A times G of phi of n minus 1 times A. None of these numbers have anything in common with n. Imagine two of these numbers were identical mod n. If GIA is congruent to GJA mod n, that would imply A times GI minus GJ is congruent to 0 mod n. So we've got to be very careful as to how I want to do this. So we know A has nothing in common with n, right? So the only way this could be 0 mod n is if this is 0 mod n. What would it mean for this to be 0 mod n? Gi equals gj. So this is relatively prime to n forced to be 0 mod n. So these numbers are all distinct. So they're all distinct residues. They're all distinct mod n. So if they're all distinct, it's the same as just multiplying g1 to g phi of n minus 1 in some other order. Right? So because they're distinct, it's just now g1, g2, g of phi of n minus 1. And this is where we're using the distinctness. So does the proof look very similar to that proof? Yeah, the proof generalizes very nicely. Lagrange's theorem from abstract algebra is an absolutely wonderful theorem. Do we need that here? No. It's almost equivalent if you're using Lagrange to using a tactical nuclear warhead, to stop a schoolyard bully. It will work, the bully will stop, but it's a little bit of an overkill. We do not need the full strength of Lagrange here. We can prove what we need directly, and we can prove it from what we've already done before. Now, what should we do? What do we do now?
Subtract the left side from the right side?
No, I don't. You could do that, but I'd prefer. Oh, okay.
What's that other way?
I'm sorry?
Subtract g1, g2.
You could subtract, but rather than subtracting, I think I'd rather do division. Because g1 is relatively prime to n, I can cancel the g1 from both sides. It's the same as subtracting, pulling out the g1 to g phi n. We can do it either way. So if I subtract, I get g1, g2, g phi n minus 1 times a to the phi of n minus 1 is congruent to 0 mod n. Either way is fine. So if I subtract, I know none of these have any factors in common with n, so I would have to have this must be congruent to 0 mod n. The other way to do this is because g1 is relatively prime to n, I can cancel g1 from both sides. I can cancel g2 from both sides. Boom, 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 boom. And so this finishes the proof. And we now have this nice generalization of Fermat's little theorem.
If we go from phi n to phi n minus 1.
Oh, I put the parentheses in the wrong spot. It's phi of n minus 1. Thank you. And so we've now generalized Fermat's little theorem. And when we get to RSA, we're going to get enormous dividends from this. This is one of the most useful theorems we can prove. Yes?
Is the question right?
Oh, sorry. Sorry, you're right. I'm sorry. I should be writing phi of n, not phi of n minus 1. Sorry. It all comes down to how you start the notation. So it should be a to the phi of n is 1 mod n. Do I start off with going 1, g1, g2, g3? Because 1 is really the 0th term. And so if I start counting with the 0th term, I go to phi of n minus 1. I'm starting here with the first term, not the 0th term. So you would often write this in a slightly different way. So we've got Euler's theorem. So this gives us information on a to a power. We'll see applications for RSA. The last part of this chapter is the Chinese remainder theorem. And so I'm not going to really go through the proof of the Chinese remainder theorem because the version they give in the book essentially has the proof in the statement. It tells you not only is there a solution to the system of equations, but here's the solution. So you just have to check and see that the solution works. And so I will state the Chinese remainder theorem. So there's a lot of different ways of stating this. So I'm saying n1 through nr are positive integers, pairwise relatively prime. So this is a stronger statement than saying that nothing divides all of them. It means no two of them share a common factor, which is a little bit stronger. Then there exists a solution to the system of equations x is congruent to a1 mod n1 dot 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 x is congruent to ar mod nr, given by x equals a1 n over n1 y plus y1 dot 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 plus ar n over nr yr, where n is the product of the n's and yi is the inverse of n over ni mod ni. Okay, so we'll talk later as to why we care about this. The proof is actually from the solution they give us. Now you could prove something maybe a little bit stronger, that this might be the only solution for x up to between 0 and n. So why is this a solution? So I want to show that this solves all of these equations. N is the product, big N is the product of all the little n's. So let's see what's going on if I look at this solution mod n1. Here, n divided by n1, there's no more n1s left over. But in everything else, I have an n1 left over. So when I look at this mod n1, so I guess I'll call this proof. Mod n1, y is just a1, I'm sorry, x is just a1 n over n1 y. But what are we told y is? Yi. We're told yi is the inverse of n divided by ni mod ni. So y1 is the inverse of n over n1 mod n1. So mod n1, this is just 1. So x is a1 mod n1. So the only thing that remains to show is that the inverse exists. Because the n's are mutually prime, or relatively prime in pairs, n divided by n1 is just n2, n3, n4, nr. That has nothing in common with n1. Since it has nothing in common, it's invertible. So all of these exist. I can write down this expression, and you just check, boom, 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 it works. So this is the system of equations. We can solve them simultaneously. The last thing which I want to end on today is, why do we care about results like this? So the first was talking about RSA cryptography. Modern e-commerce would be dead without good cryptography. So hopefully this is enough motivation. The other motivation I'll give you is a little bit more theoretical. So if you do number theory, the biggest items we like to study are the primes. And one of your homework problems was to try to generalize Euclid's argument that there are infinitely many primes, to show that there are infinitely many primes congruent to 3 mod 4. And you were hopefully able to do that. If not, I'm happy to chat. It's in the solution key, and I will eventually get you the right solution key. What if I want to do the following? Is there a prime congruent to A mod B? Just one. I just want to know, is there one prime? If I do something stupid, you should be able to tell me probably not. What would be something really stupid to do? Yes?
A is a factor of B and A is composite.
Yeah, let's say A and B are like 12 and 24. How many primes are there congruent to 12 mod 24? None. All right, so if not stupid, i.e. A and B are relatively prime. It turns out the answer is yes. there is always a prime congruent to A mod B. The only way we know how to prove this is the following. So, given B, there are phi of B, A, that are relatively prime to B. Let's let pi of x equal the number of primes less than or equal to x. If we let pi a b x be the number of primes less than x congruent to A mod B, this is approximately pi of x over phi of B. This is the tactical nuke overkill. To prove the existence of one prime, I prove not only is there one prime, there's infinitely many more, and they fall in the congruence classes to first order the same way. Therefore, there must be at least one. It turns out that doing stuff like this involves Fermat's little theorem and stuff like that. All right, so this is a good place to stop.